Perfect. And we are online.
Okay, so welcome everyone to today's seminar. It's a pleasure to introduce Mathieu Renzo, who is currently a postdoc at Columbia University at a Flatiron Research Fellow at the Center for Computational Astrophysics. Mathieu got his PhD in 2019 at the University of Amsterdam in the Netherlands. He has also been a graduate fellow in KITP at UC Santa Barbara in California, in the United States in 2017, and an INFL and LIGO summer student in Tapir at the California Institute of Technology. So thank you, Mathieu, for accepting our invitation. You may start when you're ready.
Thank you for having me. Yeah, so today I would like to talk about what we can learn about the life and death of massive stars from gravitational waves, and in particular, what the masses of the black holes that are being discovered tell us on the pulsational pair instability evolution, which has been theorized a long time ago, but only now we're getting the first uncontroversial hints that this process does happen in nature. So before I get into the details of this picture that I will explain in a second, I would like to start from the status of these fields about 6 years ago, before the direct detection of gravitational waves. So in this very famous visualization, you're seeing the masses of compact objects that we could measure from X-ray binaries. So a compact object is a accreting mass from a companion star. We look at the orbit and we get the masses. The x-axis here doesn't mean anything. It's just to spread the points apart. And the y-axis has the masses in solar masses on a non-linear scale. You can see that there is the same space between 5 and 10 as between 10 and 20. And in yellow, you have neutron stars, which are very interesting on their own and have masses below 2 point something solar masses. And in purple, you see black hole systems. And as you can see, we only had like a few handful of systems, mostly in our own galaxy, for which we had black hole masses. However, in 2015, with the direct detection of a binary black hole merger, we started having completely different systems where we could measure the masses. And since then, this panorama has completely changed. LIGO and Virgo have detected a few binary neutron star mergers, but what has really changed the most is the black hole regime. And as you can see, all these blue dots are the masses of the black holes before they merged, and they go with an arrow into the mass of the black hole resulting from the merger. And there are a few things that we can already notice, like the LIGO black holes are all on average more massive than the black holes we knew before. That's completely understood. That's because LIGO is very good at finding big black holes. And so it sees a larger volume of the universe for these guys than for these guys at lower masses. And we can start using the distribution of black hole masses to try to learn something about the evolution of the stars that form these black holes. Of course, this is not easy to do on this visualization. So let me show this data in a different form. This is from one of the LIGO second gravitational wave catalog papers, and it's showing you the merger rate per unit volume and time as a function of the mass of the most massive black hole in the binary, the biggest black hole in the binary. And as I was saying before gravitational waves, we only knew something in this first square here, and we had absolutely no idea about the y-axis. And now, already only 6 years later, we are starting to see features in this plot, like this spike here and this long tail that extends. And so in this talk, I will first discuss the evolution of stars that make these black holes and try to argue why this feature, this spike here at about 40 solar masses, is an indication for pulsational pair instability. And then in the second part of the talk, I'll focus instead, on this tail of very massive black holes that extend all the way to 85, 90 solar masses. And hopefully, before I get to this part, I will have convinced you that these black holes are forbidden, they should not exist. And there are many ideas that have been proposed to try to solve this apparent contradiction, and I'll try to give you an overview. So let me start with the first part and discuss what is this pulsational pair instability evolution and why is it important for the progenitors of black holes below 45 to 50 solar masses. And this pulsational pair instability is a process that happens in the core of an evolved, very massive star. So this means that the star is past helium core burning. You can think of this red as a carbon-oxygen core. And in this core, the instability will happen. So a little bit for computational reasons, I will show you results from simulations where we have removed the hydrogen envelope artificially. This is a numerical simplification, but there are many reasons why you might want to focus on helium cores rather than a complete star. These are very massive, so they have very strong winds that at finite metallicity would remove most of the mass. Also, massive stars tend to be in binaries, and in binaries you can have many interactions to remove the hydrogen. And finally, even if you were to keep the hydrogen on top of your star, the first time the instability kicks in, it will get rid of the hydrogen and the following evolution will proceed the same. So for this reason, keep in mind that the results that I will be showing you are based on simulations of helium cores. And this is particularly relevant if I'm thinking about gravitational wave masses, because especially if you think that the gravitational waves come from an isolated binary, the evolution of the binary before you get to the gravitational wave merger will remove your envelope, either because of a stable Roche-Lobe overflow or an unstable Roche-Lobe overflow, which always happened before the formation of a black hole. And in this cartoon, you can see that the star that collapses is always pink, which in this cartoon, it means it's a helium core. If you consider a different evolutionary path towards a gravitational wave merger, like chemically homogeneous evolution, where the two stars are spun up by tides and spin so fast that they completely mix, well, then they never develop a core envelope structure, and it makes sense to start by studying helium cores only. So on top of that, we want these helium cores to be extremely massive. And this means that just before the instability, after the wind mass loss, you want a helium core that is more than 30 solar masses. The reason for this is that this gives stellar structures that are radiation pressure dominated. This means that the star is held up against its own gravity by the radiation pressure. And when you have these conditions of radiation pressure domination, you can hit the pair instability, which produces some of the theoretically best understood supernovae. As I mentioned at the very beginning, this is not a new idea. That's been proposed in the late 60s, and there's been a deluge of papers recently because of the connection with the gravitational waves and the black hole masses. And here I also want to take a minute to give credit to Stan Woosley, who really pushed this field forward and was the first one to be able to compute simulations of this process. Okay, so let's suppose we have a star which is massive enough to have a core this big. Then as it evolves and burns fuel in the core, it will encounter the pair instability before it runs out of fuel. And this pair instability, what it does is removing photons, because photon-photon interaction produce an electron-positron pair. And this removal of photons softens the equation of state, because the pressure is only given by these photons. And if you soften the equation of state, your star will collapse a little bit and increase its temperature. And in these stars, this is a runaway process, because as you increase the temperature, you increase the rate of this reaction. And so because of the production of electron-positron pairs, this softens the equational state, and the star starts collapsing and heating up in the center. But all of this process happens while the star still has viable nuclear fuel. This is typically oxygen, but it can be also heavier nuclei. And so as the star contracts and increases its temperature, it triggers a thermonuclear explosion. And this thermonuclear explosion can have three different outcomes depending on the mass of the star. The first outcome that was studied already in the 50s is when this thermonuclear explosion releases more energy than the entire binding energy of the star. And in that case, you get what is called the pair instability supernova, where all the stellar material is dispersed and you form no compact object, no black hole, no neutron star. If you go slightly lower in mass, then this explosion is less energetic. The only thing that it manages to do is expand the core so that the burning shuts down. And this expansion of the core triggers a wave in the outer layers that can steepen into a shock and eject some mass. And after the mass ejection, which is called a pulsational pair instability, the star relaxes, emitting lots of neutrinos, losing entropy, and it can hit the instability again and circle through this loop a few more times until the consumption of fuel at step 3, the ejection of mass at step 4b, and maybe more importantly, the loss of entropy at step 5 stabilize the core. And once the core is stabilized, it finishes its evolution as a normal star, burning whatever is left to burn, if anything, and finally forming a black hole, maybe with, maybe without a visible supernova. The third possible outcome is instead for stars even more massive than the progenitors of pair instability supernovae. If stars this massive exist, then they will hit this pair instability exactly the same, and the first few steps are the same. But at step 3, there is a second instability that kicks in that cancels out the pair instability. And in particular, this is the photodisintegration instability. Basically, this burning happens at such low densities and high temperatures that every new nucleus that you form will immediately be photodisintegrated. This means that all the nuclear energy is being used to put together nuclei and then break them apart. And none of this energy goes into kinetic energy of the gas. And so in the end, you end up forming a black hole again. And so this should tell you why people talk about pulsational pair instability, black hole mass gap. You have black holes at the low mass end, whose mass is determined by the amount of mass loss here. Then you have a range without black holes due to the pair instability, no pulsations. And finally, above a certain threshold, you should get black holes again. So to have a more detailed look at this, we can really look at what are the black hole masses that we get out of our simulations. So this plot is showing you exactly that. The black hole masses on the y-axis. On the x-axis, you have the initial helium core mass, which decreases because of the wind mass loss, and then because of this pulsational mass loss due to pair instability. And on the top axis, you have the carbon-oxygen core mass, which is maybe a better metric because it doesn't really depend on the wind mass loss rate as strongly. And so here you see in blue on the left, cores that were too small to do this pair instability. And so here the black hole mass, we estimate it as the full mass of the helium core, and we have a one-to-one relationship. Then in the green points, you start having these pulses, and as the core gets bigger, the amount of mass that is lost to pulsations is bigger. And so you have this turnover in the black hole mass distribution with a maximum at about 45, 50 solar masses. Then in yellow, you hit the pair instability regime with the full disruption and no black holes formed. And for carbon-oxygen core masses of above 120, you again find black holes. And one result that I really want to highlight here is that these boundaries of 50 to 130 solar masses are actually very robust, very unsensitive to most of the physics in our stellar models. And most groups that run these simulations tend to agree on these numbers. The only uncertainty, which I will go back to at the end of this talk, is the fate of a hydrogen envelope if for some reason your star manages to keep the hydrogen envelope. And in particular, these models here in blue might reach core collapse while still having a hydrogen envelope and make bigger black holes. But the pulsational peri-instability process itself, we have a very good theoretical understanding and agreement between groups. Just to demonstrate that this result is robust, let me show you a zoom in on this plot on the bottom left corner. And this is a plot where now I'm showing you models run at different metallicities. So you can think of these as these are stars that go through this pulsational peri-instability in different galaxies. And as you can see, varying by more than 2 orders of magnitude the metallicity, the maximum black hole mass below the gap only varies by about 7%. So even this is an important result because it tells us that the mass of the black hole, the maximum mass of black holes below the gap is not sensitive to where and when the black hole were formed in the universe, which might mean that if you're able to standardize these, we might be able to use this feature in the black hole mass distribution to do cosmology as a standard siren, as opposed to standard candles like supernova 1As. There is, however, one thing to which these mass, the black hole masses are sensitive. And the only uncertainty that we were able to find that has a big role is the rate of the C12 alpha gamma reaction rate. This reaction basically governs the end of helium core burning because you, at the beginning of helium core burning, you make some carbon, and then you have a mixture of carbon and helium, the alpha particles, that can do this reaction to finish burning up helium. And the rate of this reaction determines the rate of C12 to oxygen 16 in your core. So if you lower the rate, like on the left of these plots, then you're gonna get more carbon in your core, and you can have a thicker carbon shell burning that stabilizes the core. And for this reason, the gap moves upward to higher masses. If instead you increase the rate, like on the right of this plot, you get less carbon, but once you have no carbon at all, the black hole masses are not very sensitive. And so if we can place securely the location of the gap from the LIGO data, we might be able to use gravitational waves to do very complex nuclear physics measurements that are still lacking for decades, or that have large uncertainties for more decades. The only problem here is if there are things like different channels, third generation, second, third generation mergers, etc., that can populate this gap and hide its boundaries. And I want to go back to this figure now from LIGO. And as you can see, the fact that we have a maximum black hole mass and a turnover in the mass distribution makes us expect that we should have a pileup of black holes just below the lower edge of the peri-instability mass gap. And this peak might very well be exactly that. So this peak is today the most uncontroversial evidence for pulsational peri-instability acting in nature. And of course, here I'm showing you just one of the many fits that the LIGO-Virgo scientific collaboration has used on their data. But regardless of what model you use, if the model allows for a feature, then it will prefer a feature between 30 and 60 solar masses. And so, as I said before, these old theories comes from the 60s, and only today we're getting the first uncontroversial evidence for it happening in nature. This is not because other evidence doesn't exist. For example, supernovae observations and the observations of the explosion themselves do provide some evidence, but it's always controversial. It's always debated. And the reason is that the theory and the models of this pulsational pair instability process have a wide range of predictions for the electromagnetic transients, and these predictions overlap with the predictions for different explosions, like normal supernovae or other kinds of stellar transients. And so this is why demonstrating that this process works by directly finding the explosions has been challenging. And here, just to give you a flavor of the range of theoretical predictions and the trends that these theoretical predictions predict, I'm just going to focus on two different things. The first one that I want to show you is the timing of the pulses. So when are the pulses happening with respect to the final death and black hole formation? So this plot is showing you exactly that, the delay time between core collapse and the pulse as a function of the carbon-oxygen core mass of our models. And as you can see, there is a very big range that goes from basically no delay to 10 to the 4 years. And there is also, not only there is a wide range, but there is a trend here. Bigger cores have longer delay times between the first pulse and the formation of the black hole. And this is because bigger cores have bigger explosions that drive them farther away from their equilibrium configuration, and then it takes longer to recover your equilibrium and do a second pulse and finish your evolution. And in particular, the upper limit here is about 10 to the 4 years, and that corresponds roughly to the Kelvin-Helmholtz timescale of these stars. So a full thermal timescale mediated by photons. The other thing that I want to emphasize, though, that is relevant to electromagnetic observations of transients is the top panel here, which magnifies this bottom region of the plot. And as you can see, there are many pulses expected within months from the final explosion. And this is exactly the time scale that intra-night flash spectroscopy of supernovae can probe. So if you find a supernova going off very early in its explosion, you can take spectra very early on and see if there is circumstellar material that was ejected in the past month, which could be due to this process. The other prediction that I want to show you, and that connects to what I was discussing about the black hole masses, is the mass lost per pulse. Because when the mass is lost and how much mass is lost will shape the density distribution around these stars and will influence the light curves of the explosions and maybe their spectra as well. And so here again, I'm showing you the amount of mass lost per individual pulse as a function of the carbon-oxygen core mass. And again, the range is very big, from totally irrelevant to gravitational waves, but potentially detectable, all the way to several tens of solar masses. And again, there is a trend though. Bigger cores lose more mass. That we knew already because it's what causes a turnover in the black hole mass function. But also, the first pulse seems to remove more mass than later pulses with some noise. And this is related to the kind of nuclear fuel that is burned in a pulse, because the first pulse typically burns oxygen, and later pulses will burn a mixture of oxygen and products of oxygen burning, which releases less energy. And on the top panel, you can also fit for the total amount of mass lost analytically. And I want to remind you that I'm showing you results from helium cores. So a 54 solar mass carbon oxygen core will lose 20 solar masses from the helium core. If it had a hydrogen envelope, if the hydrogen envelope goes away in the first pulse, you should add to these points the entire mass of the hydrogen envelope and have much thicker shells of material around your stars when they explode. But in the interest of time, I would like also to move on to discussing how do we make these forbidden black holes. There should be a gap. Stellar theory predicts a gap between, say, 50 and 130 solar masses, but LIGO has detected black holes in that mass range. And in particular, this whole tail that extends all the way to almost 100 solar masses should not exist if you take stellar theory at face value. And so the question becomes, how do we form these black holes? Well, first of all, these seem to be relatively rare. About 3% of the LIGO black holes, once you correct for the observational biases, are expected in this mass range. But still, since it's a very interesting range, there have been plenty of theoretical ideas that have been proposed. And before discussing one in particular in detail, I will try to give you an overview. And unfortunately, this is such a hot topic that even if I made these slides yesterday, it's probably already outdated. But you can do two things to put a black hole in the black hole mass gap. You can mess with the star so that it avoids this pulsational pair instability process, or you can mess with the black hole, assuming that it formed below the gap and then grew in mass. And among the category of things that you can do to the star, you can try to move the gap. One way I've actually already shown you is to decrease the rate of these particular reaction rates, or you can add physics to your stellar models, like other particles that will modify the core structure and prevent this instability. However, if you move the gap, you're likely to move this peak as well. So this is not necessarily a very promising avenue, in my opinion. The second thing that you can do is completely avoid the pair instability, either with stellar mergers, and this is what I will focus on in the rest of the talk, or by making the cores very small by default. And one way of doing this is to prevent mixing at the outer edge of the core. So for those that are familiar with stellar evolution, this is often called overshooting. And if you don't allow for this mixing, then the core stays small, too small to pulsate. And if you can swallow your hydrogen envelope, you can make a big black hole. The other category of things that we can do is do things to the black holes, like having them accrete mass. And this is challenging though. For example, if you put your black hole in a binary system and make it accrete mass from the companion, then your binary will typically widen. And therefore, you're not going to get a binary black hole merger within the age of the universe. So isolated binary was shown by Van San et al. Not to be a promising solution. But you can accrete from other things, like a protocluster, a halo, or you could have primordial black holes accreting from the primordial density as well. And finally, you can have multiple mergers. Say that you have two black holes below the gap, they merge and form a black hole in the gap, and then that black hole merges with another black hole. This generally requires an environment for these mergers that is good at retaining the black holes. This effectively means an environment with a high escape velocity, because when two black holes merge, they get a recoil that can get them out of their environment. And so nuclear clusters and AGN disks are typically the ones that have been considered the most. And just before I go into the details of the stellar merger scenario, for completeness, there's also the possibility that these forbidden black holes we have mislabeled their masses. In particular, if these would be very eccentric binary black hole mergers, we don't have good waveform models for these, and so we're not very good at estimating their masses. There could be gravitational lensing effect, although the rate is a bit high for that. Or depending on what priors you use on the black hole masses, you can also find solutions where the black holes are not in the gap, but they have one black hole above and one below the gap. But just because it's a very hot topic and LIGO is finding and will continue finding these black holes, I think it's interesting to look a little bit more in detail to some of these scenarios to see what we can learn and if we can confirm that. And in particular, I would like to focus on the stellar merger scenario, which uses dynamics in a cluster to merge stars and create a weird stellar structure that can avoid the pair instability. So the idea was originally proposed by Spera et al. In 2019, based on n-body simulations of clusters. And the way you create a stellar merger that avoids the pair instability is to take two stars that are not massive enough to go pair instability. And as soon as the first star finishes its main sequence, so it has formed a helium core, you merge the stars. But you assume that the merger doesn't change the core, which is maybe not what we would expect from merger simulations. You would expect the two cores to merge, and around these two cores, the two envelopes to merge. But here the assumption is that we only get the core of the first star, and the second star only contributes to the envelope. It contributes its total mass to the envelope. And then you've made a weird star, which has a lot of mass, in this cartoon about 100 solar masses, but a small core that is too small to go pair unstable. And then you decide that this star holds on to its mass for the entire remaining lifetime and collapses to a black hole, swallowing its entire hydrogen envelope. And that gives you a big black hole, which then you're in a cluster, this big black hole can find another black hole and finally form a gravitational wave event. In this scenario, however, there are a few assumptions that require further testing. The first one I actually already discussed a bit, and it's the merger process, which here it's extremely simplified, and it assumes that there is no mass loss during the merger, and more importantly, no rejuvenation. By rejuvenation, I mean modifications in the core structure, which are things that we would expect. Then there is the assumption that this weird star of 100 solar masses with a small core holds on to its mass for its entire evolution. And now when we see 100 solar mass stars in the local universe, they tend to be pretty violent and do bursts of mass loss. This is not considered here. Finally, there is the fate of the envelope. Can the black hole swallow all of the hydrogen envelope? And the last challenge is the one that has been worked out in the literature is, well, do we have a rate of these objects that is significant enough from our simulations? And if you have a sufficiently dynamically active environment, this seems to be the case. So what I try to do here is to follow the assumption of this scenario and make a model of this merger star to study its evolution. And I will try to go one by one in these assumptions here. And the first problem is the mass and angular momentum budget. And why are these problems? Well, when you have a merger, especially in a cluster, this might be a merger that is a head-on collision. And if you have these dynamical mergers, typically, as a function of the impact parameter, you expect a certain amount of mass loss. The more head-on the collision is, the more mass you lose, with about 10% as a cap. And this is informed by simulations of low mass stars where radiation effects are neglected. So this amount of mass loss of a few percent up to 10% should be considered a lower limit, not an upper limit or a realistic estimate, because very massive stars that are very radiation pressure dominated should lose mass also because of radiation. We can still do a very crude estimate and calculate the kinetic energy that we have in our cluster to smash the two stars together and see what amounts of mass that energy might be able to rule out. So here, this is the binding energy profile of two stars that are going to merge as a function of mass. So this is the core with the highest binding energy, and this is the surface. And if you estimate the kinetic energy in the cluster with the dispersion velocity of the cluster, you get this dashed line. And so there is a very small amount of mass loss that can be lost. But this is a very generous estimate, because when the two stars will collide, they won't reach each other with the dispersion velocity of the cluster. They would reach each other with their escape velocity, which is much higher and would remove more mass. But for the sake of following the scenario as proposed, I will assume that there is no mass loss in the merger, although this is a very crude assumption. The second problem is the angular momentum. Unless your collision is perfectly head-on, you will have some relative angular momentum of the two stars, which you have to conserve, and so you have to put it somewhere. And if you put it close to the surface of the star, you will have centrifugally driven mass loss, which decreases your total mass, and that's not what you want, because you want to form a black hole in the end in the peri-instability mass gap. If instead you put this angular momentum close to the core of your merger product, then you will have rotational mixing that can make the core grow, and you will hit the peri-instability, because by definition of the scenario, we're just below this threshold, so it doesn't take much growth of the core to reach the peri-instability regime. But again, for the sake of argument and just following the assumptions of this scenario, I will assume that my merger product is non-rotating. With these two assumptions about the merger, which again, for emphasis, are very crude and should be tested further, I can run a MESA model of the merger itself. I can construct it by a stellar structure by hand and let it evolve. And to do this, I first evolve two stars up to the point where they merge. And this plot is showing you the chemical composition as a function of their mass coordinates. So 0 is the core, the right end is the edge of the envelope. And you see here, these profiles are plotted at the end of the main sequence of the star on top. So its core is pure helium, by definition of the main sequence of a star. But by this time, the second star, which is also very massive, has about 75% helium in its core. And this is because massive stars all have very similar lifetimes of about 3 million years. And so if they started their evolution together, they will get to the end very close to each other. And now the problem becomes, where do we put this helium in our merger? Physically, I would expect it to sink on top of the helium of star 1 and make a very big core that will go peri-instability. But the scenario forbids this. So where do I put it? We can make two models that bracket the range of possibility. In the first model, we're going to take star 2 and fully mix it in the envelope of star 1. This is a very crude approximation because it means that I'm mixing material from the core all the way into the envelope of the surface of star 1. And these two layers will have very different entropies. It's very difficult that they would mix in nature. And if you do this assumption of completely mixing star 2 in the envelope of your merger, you get these solid lines profile for the product of the merger. The other possible case is that we completely neglect the evolution of star 2. This would correspond to a cluster when you allow star formation to be spread out over at least the lifetime of star 1, and you have fine-tuned the merger so that as soon as star 2 forms, it immediately merges with the evolved star 1. And this would give you the dashed lines, which are less helium enriched or not helium enriched compared to the initial composition of the stars. And now that I have these very, very simple toy models for the merger, I can let them evolve and test whether the star would hold on to its mass. And so this is an HR diagram, so luminosity versus effective temperature in the wrong direction of these two merger models. The evolution goes from left to right, like in a normal HR diagram, and there is one dot every 500 years here. The blue curve is for the model where we completely mix the secondary. So it's helium rich, and that's why it's more luminous. The other one, the red curve, is instead the model where we neglect the evolution of the secondary. And the point here is that these stars spend a long time in this gray box. This gray box, called the S Doradus instability strip, is where we observe stars undergoing huge eruptions of mass loss. These eruptions are called luminous blue variable eruptions. And there are theoretical arguments why a helium-rich star might be more prone to them. And then these stars evolve past this dotted line, which is the Humphrey-Davidson limit. And there is a region of the HR diagram where we don't see many stars, maybe because they don't spend much time there. And one of the reasons is that these stars in that region become super Eddington. So basically the radiation pressure cancels out gravity and the star should not be in hydrostatic equilibrium anymore. And this is what's happening at these spikes here. And this is another indication that our models would like to lose mass dramatically. And just to hammer down this point, I also want to put in your mind the connection with Eta Carinae. Eta Carinae is a very famous massive star in our own galaxy, so at relatively high metallicity, that in the 1900s had giant outbursts of mass loss with tens of solar masses lost. And the best models we have today for Eta Carinae from Hirai et al. Do rely on a merger between very massive stars to explain the outbursts. So here, the assumption that there would be no mass loss during the evolution of the star is maybe problematic, even if you follow the assumptions of this scenario for the merger itself. The other thing that I want to very briefly discuss is what is the envelope fate at core collapse. This is necessary if you want to make a black hole in the gap with a star that has a very small core and a very fat envelope. But when a black hole forms, there are many ways in which it can lose mass because of the neutrinos that are flying away and carrying away energy, because of rotation of the star, which can power disk formation and jets, or because first you form a very small black hole, and then you have all of the envelope falling onto this black hole and releasing gravitational energy that can power late fallback powered explosion. And we need to consider these. These are all these mechanisms are an open question for all kinds of supernovae, including those that avoid the pair instability and the pulsational pair instability supernovae. And with my models, although they are just toy models based on a crude simplification, we can try to test some of these. And the first one I can test is the mass loss due to neutrinos. Here, the trick is that when the core collapses and forms a black hole, its mass is not the core mass, but it's the core mass minus the energy that neutrinos have taken away on a certain time scale, which is usually maybe up to a second. And there are layers of the star that have a free fall time scale that is much longer than the time scale for the emission of these neutrinos. And so for those layers, this is an instantaneous change in the mass at the center. The gravitational potential decreases, and these layers can then expand and fly away. And this mechanism is thought to remove the hydrogen envelope from a red supergiant that forms a black hole, even without an explosion. However, my merger models, because of their small core, they're very blue when they explode. And so here you see a simulation of this process starting from my merger models, and you see that the amount of mass lost is very small. But this is because the mergers are blue, and the mergers are blue because of the assumptions that I did when constructing the merger. The other thing that I can test is whether there is enough rotation in my models to power an explosion. And my models, I remind you, are non-rotating, or neglect rotation. But even if you're non-rotating, in the convective regions, there can be blobs of matter that carry some angular momentum stochastically. And can these angular momentum power an explosion? So here you're seeing the random angular momentum that is stored in these convective regions in red as a function of the time that it would take for that region to fall on the black hole. And in blue and orange, you have the angular momentum of a black hole that starts as basically non-rotating and then accretes mass. And from the fact that the red is always below the blue, we don't expect any disk formation. This is because the disk would form only if the material falling in would have too much angular momentum to directly fall in and would circularize into a disk. So this doesn't seem to happen with my models. But again, this is because they're blue, so very compact in radius, and this doesn't give them a huge lever arm to build up angular momentum. But in a merger, we should expect some rotation to be there. So also these should be tested further with better merger models. And then the last very quickly problem is how do we pair these black holes? Because if everything goes well up to there, we've made one big black hole. We need two to have a gravitational wave event. And this is where the cluster dynamics help you. And in this simulation, the rate that they have found is fairly high, even a finite metallicity, which is suspicious to me. But if you want to apply these to the most massive binary black hole that LIGO has seen, since both masses are in the pair instability black hole mass gap, then you need this process to happen twice in a cluster, and these two black holes should merge. And given the variety of other options that are available, I would personally not consider this the most promising explanation. And so just to conclude, because I think I'm running out of time, the main take-home points that I wanted to leave you with is that the detection of gravitational waves is really changing the landscape of black hole masses that we know of, and is providing the first uncontroversial clues that pulsational pair instability happens in nature, which corroborates debated evidence from supernova transients. And the detection of this tail of very massive black holes that should be forbidden is hinting at the fact that there might be other processes that can make binary black holes that are not just isolated binaries. It probably requires dynamical interactions to explain these black holes. And if you want the dynamical interactions to make a weird stellar progenitor for you so that that progenitor can make a big black hole, then you definitely want the whole hydrogen envelope to fall when you form the black hole. And this is something that we don't fully understand yet and should have more studies about. And that's pretty much what I wanted to tell you. Thank you.
Thank you so much for your talk, Mathieu. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them in the comment section below. See you next week for a seminar on cosmic rays. Goodbye.